Hey everyone, this is Karthik Jokbadi, and this is my Physics 2212 Lab 4 for circuits. So, introduction, the purpose of this lab is that we are just analyzing various behaviors in circuits involving things such as series, parallel circuits, and using capacitors and resistors. Physics principles for this, we have V equals I over R, so voltage equals current over resistance, and we have capacitance equals charge over voltage, also area times epsilon naught over D. So sum of potentials around the circuit is also 0. Results for that, we found a bunch of resistances which were calculated in part 1, which we will see later on, and the actual RC that we got was 6.135 seconds, and the estimated RC was 6 seconds. We will see what this is in the future slides. Initial conditions, system was basically just like the circuits we create. There weren't really any actual systems here, and the surroundings there was nothing because this was in an online environment. Initial conditions for each part, there are specific resistance values we had to set our bulbs to, and specific voltage values we had to set our battery to, and there were different setups that we had to use for different parts of the lab. So for part 1, we had to create a series circuit over here with two 1.5 volt batteries and then two resistors, one of 47 ohms and one of 100 ohms. So predicting I1 and I2, they both would have these two ammeters would have the same current in them because this is a loop, and we calculated by summing the total voltage divided by the total resistance and got 0.02041 amperes. And observed here, we can see it's 0.02 amps, and if it's reversed, it's negative 0.02. And then when we replace the ammeter with a voltmeter, the current was 0 because this is an open circuit, but the voltmeter is 3. Because it's an open circuit, there is no current, but the voltage that we get here is from the two batteries. And here's our setup we created in our lab of this part. And then we calculated potential differences between different parts of this series circuit. So we calculated from B minus A, which is 3 volts, and then C to B was 0, which is from here to here. And then we basically just went around the whole circuit to find different potential differences at different values. And then when we summed all these together, we got that it was 0 volts for a total potential sum, and that makes sense because we made a round trip around the whole circuit. And the recorded current was 0.02 amperes as usual. It was consistent throughout. We also made this graph over here of the voltage at different points along the circuit. So it started off at 0, and then we can see it increased, stayed constant, decreased a little bit at this negative 0.96, stayed constant at 0, decreased by negative 2.04 over here at the bigger resistor, and then it was 0 for the rest of the circuit. Attaching a voltmeter doesn't change the current because of its high resistance, so that's why it doesn't alter the current flow. And then if we replace the voltmeter with an ammeter next to the 100 ohm resistor, the current changes from 0.02 to 0.06 amps because the path is split and some of this current is flowing through here, which isn't going through the resistor. Therefore, the current increases. And then we just calculated resistance using the potential differences at the various points for like the 47 ohm resistor, the 100 ohm resistor, the wire, and the ammeter, and we got these values for our resistances. For part 2, we basically had to get a battery, 10 ohm bulb, and a capacitor, and we just checked how charging and discharging works and recorded the time. With the 10 ohm bulb, it was 18.94 seconds to charge and 18.91 to discharge. For a 20 ohm bulb, it was 35.24 seconds to charge and 37.58 seconds to discharge. So using this equation over here, we found the potential difference at certain points and divided by the original potential value. And using this equation, we were able to find this RC value. The RC value basically represents the time constant of the circuit, so it's measured in seconds. So making this linear line, we get our y's natural log of delta V over delta V naught, and then we get our x values to be time, which is our t. So the slope of this will be negative 1 over RC. So with this, we know that the slope here is negative 0.163. So just solving around for this, we get that the RC from the experiment was 6.135 seconds. And using the expected calculations, we just do capacitance times resistance. So 0.2 farads by 30 ohms, which is 6 seconds. And these two are pretty similar. Here was our physical creation of this part of the lab. Discussion. So the model and estimated values were pretty similar, and there was minimal difference for the time constant, but there are rarely also any potential sources of error because of it being online. The only potential error is probably from when I was recording the time of the charging and discharging, because I had to turn on the circuit and then go over and turn on the timer, which is two separate instances which could have some difference. What if questions, if we were doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter, well, basically the real life ammeter would have some resistance to it and the current would decrease. if you were doing this lab in real life and use a real battery to charge a real capacitor with no resistor in the circuit. So the capacitor would charge almost immediately because there is no resistance in circuit, so there's nothing slowing down the current flow. How quickly would our ideal model predict the capacitor to reach full charge? It would basically be almost instant. That is all. Thank you.